So we were talking about how to predict the maximum theoretical efficiency of an engine. And Mr. Carnot said that you can determine the theoretical efficiency of an engine by focusing on the temperature in the high region, the gasoline region, and the temperature in the lower, the exhaust region, and making this temperature difference as big as possible. So the theoretical efficiency of an engine depends on actual Kelvin temperatures, and the actual efficiency that you get in real life depends on looking at the joules. How many joules I get from my gasoline versus minus how many joules I waste going out my exhaust system, etc. So the theoretical maximum efficiency is named after Mr. Carnot, and it's called the Carnot efficiency, oftentimes written as a lowercase e with a c. And this is the Carnot efficiency equation. So there are two equations for efficiency. The theoretical efficiency, the best I can get, and then what I actually get in real life. So I want to help you better understand what these equations are, what they mean, and the difference between them. And I do that at this video link. And in this link, I go through two example problems with you, which are number 7 and number 8 in your homework. It actually might make the most sense if you pause right now and actually go and do these two examples while this is fresh on your mind. All right, so the last thing that I want to say about this heat engine thing is that mathematically then, because of the equations for efficiency, it shows that a heat engine can never be 100% efficient. We are never going to have a 100% efficient engine. The best that we can do is try to improve whatever efficiency that we have. And I'm sure that is what engineers all over the world are trying to do. Okay, we have one last thing to talk about in terms of the second law of thermodynamics, which has a very different implication. It has nothing to do with heat engines. And that's this last statement, which we'll take up on the next slide here. All right, it says that natural processes increase the entropy of the universe. So this is the direction of natural processes. Natural processes will go in a direction that increases the entropy of the universe. So another word for entropy is disorder. So what happens in real life is things that increase the disorder of the universe. For example, let's say somebody gives you a birthday cake. It is the prettiest, best looking birthday cake ever. So you set it on the counter and you decide you're not going to eat it. You're just going to get up every day and you're just going to look at it. But that birthday cake is never going to look as good as it did the first day. By day 3, day 5, day 10, day 100, it's going to look worse and worse and worse over time. Maybe the cake's going to start to sink. Maybe the frosting's going to start to melt. But it's never going to look better when you wake up the next day. My next example, maybe you have some dinner plates. And you have a great set of dinner plates, but they're never going to be better than they are today. As time goes on, they're going to get maybe more scratched, more chipped, cracks. One may even break. They're going to naturally get more disordered over time. You clean up your bedroom. It's beautiful. But over time, it's not going to get more clean if you do nothing. It's only going to get less clean. So naturally, things always become more disordered. But there's kind of a cool implication from this, because it means that entropy can be used to show the direction of time. So consider the nursery rhyme Humpty Dumpty. So Humpty Dumpty sat on a wall, Humpty Dumpty had a great fall, blah, blah. So because of that, you should be able to look at these pictures of Humpty Dumpty and put them in order just from your concept of entropy. Like, I don't think Humpty Dumpty, who's all broken and his egg is squirting out and he's cracked, I don't think he's going to put himself back together again and climb back up on the wall. Like, that would be against the concept of entropy. So that implies that time is a real dimension. So supposedly in our universe there's lots and lots of dimensions. I don't know how many. But we can now say that we know 4 of them: length, width, height, and time. Time is truly a dimension as predicted by the second law of thermodynamics. All right, there's also another interesting and important implication. It says energy also gets more disorderly over time. And that means that when we convert energy into different forms, the remaining energy can always do less useful work. For example, we could have water going over a waterfall, and then we take that water going over the waterfall, we harness it to build the electrical plant, and we get electricity. And then we use that electricity to make toast. And then we eat the toast to get energy so that we can run around the block. And then we get down and run around the block. We keep having different types of energy, but after that's all done, I can't go back and eat more toast because I have no way after running around the block to turn that into toast. And so my energy keeps degrading over time. And that's an important concept because the first law of thermodynamics says that the total quantity of energy in our universe is always going to be constant. But because of the second law, the quality of that energy is always going to be downgraded. It's going to be less useful to us. Once I burn everything up and get the heat out of it, I burn up all the gasoline, I burn up all the coal, I burn up all the oil. Now there's nothing else to burn up. And pretty soon we come up with something that some scientists have called heat death. Heat death means that we still have all of the joules in the universe that we've always had, but they have been downgraded now to the very, very, very lowest form of energy. And the only thing we have left is internal energy, because internal energy is the lowest form of energy. And internal energy is just bouncing molecules. So that's what this beaker here is supposed to be showing. I put a beaker at sea level to show you that, actually I won't call it a beaker, let's call it a container of gas. It's at sea level, which means it has no potential energy. It has no kinetic energy, it's not moving. I can't get heat energy out of it, I can't burn it. I can't do anything. All I have is bouncing molecules. They have joules, but I can't do anything with this joules. I can't eat them to get food. I can't plug them in to make toast. I just have a useless form of energy. And that is called heat death, a possible way that our universe could end when all of our joules turn into internal energy and I can't do anything else with them. So that's a sad ending of our second law of thermodynamics. All right, the last thing that we have to look at then is the third law of thermodynamics, which is rather short and sweet. And the third law says there is no further disorder when all motion stops. I mean, picture that. Everything stops. It's not getting out of order anymore. But that's impossible because the second law says that entropy will always increase. So since entropy cannot be zero, it is impossible for all motion to stop. And that implies that no process or substance can ever reach absolute zero, because in absolute zero, everything would stop. So basically, the third law of thermodynamics says that we can never reach absolute zero. It's a cooling point that we can approach, but we can never get there. And absolute zero is minus 273 Celsius, or approximately negative 460 Fahrenheit. So, in summary, the zeroth law in general tells you when heat will flow or when it won't. The first law connects heat to energy and gives us some conservation of energy statements. The second law explains the natural direction or the direction of natural processes. And the third law defines the minimum temperature of the universe. And I think you can see what Einstein was saying, that those laws are all so very different. They apply to a lot of different things. And, it seems like we were all over the place. And that's why Einstein thinks the laws of thermodynamics are so profound and important, and they are probably not going to be overthrown because they apply to so many different things in our lives. All right, I hope this provided a decent overview of the laws of thermodynamics. It really is a difficult, complex topic in college where you can have a whole class devoted to thermodynamics where we spent one day or at least one lesson on it. So it at least gives you a taste of what kinds of things are in that topic area. Okay, I'm going to stop here.